A camera looks at a handwritten number. A radar signal bounces off an object. A laboratory instrument measures the optical fingerprint of a pharmaceutical sample. To a normal computer, these are three different worlds. The image is made from pixels. The radar arrives as a changing radio frequency waveform. The chemical sample appears as a spectrum, different wavelengths rising and falling according to the material being measured. Each normally requires its own sensor electronics, conversion hardware, and processing pipeline. But researchers in China have built one photonic intelligence chip designed to handle all three. Instead of forcing every signal through a conventional digital processor first, the system converts images, spectra, and radio frequency signals into a common optical language, light. Those optical patterns enter the chip through a single fiber. They are separated, weighted, and processed by microscopic waveguides. The result passes through an optical neural network and reaches a classification output with a measured response time of just 1.33 nanoseconds. 1.33 billionths of a second. The chip successfully classified handwritten images, recognized pharmaceutical spectra, and distinguished radar targets, and it performed part of that computation using only 29 femtojoules per operation. A femtojoule is 1/4,000,000th of a joule. This does not mean the chip can understand every image, identify every chemical, or operate a complete autonomous vehicle by itself. It is still a research prototype. The laboratory setup includes external light sources, amplifiers, and test equipment that would need to be reduced or integrated before practical deployment. But the achievement points toward a new kind of edge intelligence. A sensor may no longer need to capture information, digitize everything, send it to a processor, and wait for a response. It may process the signal almost immediately, using the physics of light before the data ever becomes a conventional stream of digital numbers. The delay hiding between a sensor and AI. Modern sensors generate enormous quantities of analog information. A camera receives changing light intensity. A radar antenna detects reflected electromagnetic waves. A spectrometer measures how materials absorb or reflect different wavelengths. Nature produces analog signals continuously. Computers prefer digital numbers. So before a conventional AI model can process the information, the sensor output must usually pass through several steps. First, the analog signal is sampled. Then, an analog to digital converter turns it into numbers. Those numbers move into memory. The processor retrieves them. Software reorganizes the data into a format the AI model can accept. Only then does inference begin. Each step adds delay. Each conversion consumes energy, and each movement of data creates another bottleneck. This may not matter when a cloud server has several seconds to analyze a photograph. It matters enormously when a robot must avoid an obstacle, a radar system must identify an approaching object, or a medical sensor must react immediately to a changing signal. At the edge, milliseconds matter. Sometimes microseconds matter. Researchers therefore want to move intelligence closer to the sensor, not inside a distant data center, not after a long digital pipeline, directly where the signal first arrives. The Chinese team's Photonic Edge Intelligence Chip, called PEIC, was designed around that goal. One chip, three different languages. The central problem was not only speed, it was compatibility. An image is spatial. Its information is arranged across two dimensions. A chemical spectrum is spectral. Its information is distributed across wavelength. A radar signal is temporal. Its information changes through time. These data types do not naturally fit into the same computing architecture. Trying to process all three with one ordinary analog circuit would be like asking one translator to interpret a photograph, a melody, and a weather map using the same alphabet. The researchers solved this by converting every input into a broad optical spectrum. They call the process modal fusion. For image data, the system uses a scattering structure. The image passes through an optical setup that converts spatial patterns into a unique spectrum. A different image creates a different spectral fingerprint. For chemical data, the input is already spectral. A pharmaceutical sample can absorb or reflect light differently depending on its composition. For radar, the radio frequency waveform is used to modulate an optical carrier. This converts time-domain radar information into sidebands distributed around an optical frequency. Three original formats. One optical representation. Once every signal becomes a spectrum, all three can travel into the same chip through one fiber. That is the first major innovation. The chip does not need a separate entrance for every type of sensor. It asks the sensors to speak light. Why light changes the computation? Electronic processors perform operations by moving and switching electrical charge. They are extraordinarily capable, programmable, and mature. But moving charge creates resistance and heat. Digital systems also process many tasks through sequences of clocked instructions. Light behaves differently. Multiple wavelengths can travel through one waveguide at the same time without being processed one after another. This is called wavelength parallelism. Imagine one road carrying cars of many colors. An electronic system may inspect each car separately. A photonic system can route all the colors simultaneously according to their wavelength. That makes optical computing attractive for mathematical operations that repeat across large datasets. Neural networks depend heavily on those operations. They multiply inputs by weights, combine the results, and pass them through nonlinear functions. A conventional chip performs those multiplications electronically. A photonic chip can encode values into light intensity or phase, then let interference, routing, and detection perform part of the mathematics physically. The answer emerges from how the light propagates. In the PEIC, the first major processing stage is built around an arrayed waveguide grating. It is one of the most important components in the system. The prism built inside a chip. An arrayed waveguide grating, or AWG, behaves somewhat like an advanced microscopic prism. A normal prism separates white light into colors because different wavelengths bend differently. An AWG performs a related function, using many waveguides with carefully controlled lengths. Light enters the device and splits across an array of paths. Each path is slightly longer than the previous one, but light waves accumulate different phase delays. When those paths recombine, different wavelengths interfere constructively at different output ports. One wavelength travels toward one output. Another wavelength travels somewhere else. The researchers' AWG contained 185 arrayed waveguides and occupied roughly 1.5 by 1.5 millimeters. It separated the optical spectrum into channels spaced 100 gigahertz apart. But the component did more than detect wavelengths. The team also used it as a convolution engine. Convolution is one of the fundamental operations in machine vision and signal analysis. A small pattern, called a kernel, moves across the input and measures particular features. One kernel may respond strongly to edges, another may detect curves, another may identify a repeating frequency pattern. Instead of performing those calculations sequentially in digital logic, the PEIC weights different parts of the optical spectrum and routes them through the AWG. The optical energy arriving at each output represents the convolution result. The chip is sensing and computing in the same structure. That combination avoids moving raw sensor data into a separate processor before useful features can be extracted. Why 29 femtojoules matters. The researchers estimated that the sensing and convolution stage consumed around 29 femtojoules per operation. The number is almost too small to visualize. 1 femtojoule is 0.000000000000000000000001 joules. A common household light bulb uses tens of joules every second. The energy used in one optical operation is a microscopic fraction of that. This does not mean the complete laboratory system runs on 29 femtojoules. External lasers, amplifiers, control electronics, and supporting equipment consume far more power. The number applies to the optical computation itself. That distinction matters. A chip can have an extremely efficient core while the complete system remains bulky or power-hungry. Still, core efficiency is important because edge devices live under strict limits. A drone cannot carry a data center power supply. A wearable sensor cannot become hot against the skin. A small robot cannot devote most of its battery to converting and moving sensor data. If optical pre-processing can reduce the amount of digital work required later, the entire device may become more efficient. The light does not need to solve every problem. It only needs to remove enough work from the electronic processor to justify its presence. The part that makes it a neural network. Convolution alone is not enough. Neural networks also need nonlinearity. Without a nonlinear activation function, multiple processing layers collapse mathematically into one large linear transformation. The network cannot learn complex decision boundaries. Electronic AI chips implement nonlinear functions with transistor circuits and software instructions. Optical systems find this more difficult because light propagating through ordinary waveguides is naturally linear. Double the input, and the output usually doubles. The PEIC uses a nonlinear activation layer built from photodetectors and microring modulators. The photodetector converts optical power into an electrical response. That electrical signal controls a ring-shaped optical device, producing a nonlinear change in the outgoing light. After this activation stage, a fully connected optical layer combines the extracted features, and produces the final classification result. The output is physical. The researchers determine the result by identifying which output port receives the highest optical power. No additional digital post-processing is required for the final decision. That makes the system an end-to-end optical neural network, rather than just an optical filter connected to a conventional classifier. What 1.33 nanoseconds really means. The measured response time of the nonlinear activation unit was 1.33 nanoseconds. That number represents the critical response inside the optical neural network pipeline. It is not the same as saying the entire laboratory can classify 751 million completely independent images every second. The present proof-of-concept system operates in approximately the 100 MHz range. That means its practical repetition rate is closer to 100 million cycles per second. Still fast, but different from the simplest interpretation of 1.33 nanoseconds wide a gap. A complete system includes modulation, signal preparation, optical propagation, control, and repeated operation. The nonlinear ring modulator relies on carrier injection, which limits how quickly the full architecture can reset and process the next sample. The optical input itself can carry enormous bandwidth, potentially in the terahertz range, but the current nonlinear stage limits the full system's operational rate. Think of a warehouse with an extremely wide entrance but a smaller sorting station inside. Huge amounts of material can arrive. The sorting machine determines how quickly completed packages leave. Future nonlinear optical devices could increase that rate. For now, the measured nanosecond response demonstrates extremely low latency, while the system-level rate remains around 100 MHz. Both numbers are valuable. They simply describe different parts of the machine. Test 1. Recognizing images. For image classification, the researchers used handwritten digits. These are the familiar black and white numbers often used to test machine learning systems. The image was displayed through an optical setup and projected onto a random scattering chip. The scattering structure transformed the two-dimensional image into a spectral fingerprint. A handwritten 3 produced one pattern. A handwritten 8 produced another. Those spectra traveled through the fiber and into the PEIC. The chip extracted features using the AWG-based convolution stage, passed the signal through nonlinear activation, and produced a classification output. This approach is unusual because planar photonic chips struggle with two-dimensional images. A chip waveguide naturally guides light along one direction. Routing every pixel of a large image into separate paths would create a complicated maze of connections and crosstalk. The scattering approach compresses spatial information into the spectral domain. Instead of giving every pixel its own road, it transforms the entire image into a unique combination of wavelengths. The chip then analyzes that combination. It is less like looking at the image directly, and more like identifying the echo the image leaves in light. Test 2. Reading pharmaceutical spectra. The second task involved drug spectrum recognition. Different pharmaceutical samples produce different spectral signatures. A material may absorb strongly at one wavelength and weakly at another, creating a pattern that functions like an optical fingerprint. Traditional analysis may digitize the entire spectrum and send the values into a computer. The PEIC receives the spectral data in its native optical form. No image conversion is required. No radio frequency modulation is required. The spectrum travels directly into the chip. The AWG separates the wavelengths and performs the weighted feature extraction at the same time. This is one of the clearest examples of the architecture's advantage. The sensor output and the computing medium are already compatible. Light measures the sample. Light carries the information. Light performs much of the classification. Potential future uses could include compact pharmaceutical inspection, environmental monitoring, and wearable biochemical sensing. But the experiment did not prove that the chip can identify every unknown chemical. It classified samples within a defined research dataset. General chemical analysis would require larger training sets, careful calibration, and robust handling of noise and temperature changes. Test 3. Classifying radar targets. Radar presents a completely different challenge. A radar system transmits electromagnetic waves and measures how they return after hitting an object. The returned signal contains clues about shape, distance, motion, and orientation. Traditional radar processors digitize the waveform and perform signal processing operations electronically. That can consume significant power and add latency. The researchers modeled radar returns from different target geometries. These time-varying electrical signals drove an electro-optic phase modulator. The modulator placed the radar information onto light by creating frequency sidebands around an optical carrier. A more complicated radar waveform produced a different optical spectrum. The PEIC then classified the target by analyzing those spectral features. This approach could eventually support robotics, autonomous navigation, and compact sensing platforms. A machine could receive radar data and begin extracting target information almost immediately, without first sending every sample through a large digital processing chain. Again, the current experiment was controlled. The radar signals were modeled and generated using laboratory equipment. A real outdoor environment introduces rain, interference, multiple reflections, and unexpected objects. Practical deployment would require testing under those conditions. The chip can also learn. The researchers demonstrated both supervised and unsupervised learning. Supervised learning uses labeled examples. The network sees an input and is told the correct answer. It adjusts its internal weights to reduce future errors. Unsupervised learning works without explicit labels. The system searches for structure or clusters inside the data. Supporting both approaches matters because many edge environments do not provide perfectly labeled information. A sensor may encounter patterns that were never categorized in advance. The optical chip's weights are controlled through programmable phase-shifting elements. An FPGA-based electronic framework supplies control voltages, allowing the researchers to adjust the network during inference and training. This reveals an important truth about photonic AI. The system is not purely optical. Electronics still configure the chip, calibrate components, and control its weights. The advantage comes from assigning the right task to each domain. Electronics provide flexibility and memory. Photonics provides parallelism, bandwidth, and low-latency signal processing. The future may not belong to light instead of electricity. It may belong to systems that use both where each works best. What is still outside the chip? The laboratory demonstration relied on several external components. A broadband optical source generated the light, a programmable wave shaper created controlled spectra, an optical amplifier increased signal strength, a spatial light modulator helped generate image inputs, a waveform generator and phase modulator produced radar signals. These machines are useful for research because they can simulate many sensors and inputs. They are not intended to sit beside the chip in a finished robot. In a practical system, a camera, spectrometer, or radar front end would feed signals into a smaller integrated optical interface. The researchers also note that weak real-world signals may require amplification. Their current experiment used an external erbium-doped fiber amplifier. Future versions could integrate optical gain into a silicon nitride photonic circuit, reducing the need for bulky external hardware. That path is technically plausible. It is not yet completed. The chip at the center is compact. The entire laboratory around it is not. This is common in early semiconductor research. The first transistor needed a room of test equipment. Commercial value arrives when the surrounding system shrinks. Why this could matter most at the edge? Cloud AI can tolerate complexity. A data center has powerful cooling, large power supplies, and racks of supporting electronics. Edge devices do not. An autonomous drone has limited battery capacity. A medical wearable must remain small. A factory sensor may need to react without depending on an internet connection. A vehicle cannot send every radar reflection to a distant server before deciding whether to brake. These devices need local intelligence, but local intelligence creates a trade-off. More processing increases power consumption. Lower power often means slower response. Photonic edge computing aims to weaken that compromise. Raw analog information can be converted into an optical spectrum, processed in parallel and classified with extremely low latency. Only the final result may need to reach the electronic controller. Instead of sending a complete radar waveform to the CPU, the optical front end could report a target category. Instead of digitizing every point in a chemical spectrum, it could report whether a sample matches a known pattern. The processor receives less data. The device responds faster. The battery lasts longer. That is the vision. The honest catch. The PIC does not replace a general CPU, GPU, or AI accelerator. It is specialized hardware. Its strength comes from performing a limited set of operations extremely efficiently. Changing the task requires new training and reprogrammed weights. Some applications may require different optical interfaces. The chip's demonstrated network is also far smaller than the giant models used in modern generative AI. It is designed for classification at the edge, not for writing essays or generating video. Accuracy must remain stable outside the laboratory. Photonic components can drift with temperature. Manufacturing differences can change phase and transmission. Calibration circuits can correct some variation, but they add complexity. The 1.33 nanosecond figure should also be interpreted carefully. It describes a measured component response within the network, not the entire end-to-end world-to-decision time of a finished product. And while 29 femtojoules per operation is excellent for the optical core, the complete system's energy consumption includes light generation, amplification, and control electronics. The research proves a powerful architecture. Commercial engineering must prove the product. My take. My view is that the most important part of this breakthrough is not the 1.33 nanosecond number by itself. It is the decision to unify very different sensors before computation begins. Images, spectra, and radar signals normally travel through separate pipelines. The researchers converted all three into one optical language and fed them through one photonic neural network. That could be more important than building the fastest possible chip for only one sensor. Real machines use multiple senses. A robot may need a camera in daylight, radar in fog, and chemical sensing in a hazardous environment. Today, each sensor often brings separate converters, processors, and software. A common optical intelligence layer could simplify that architecture, but the phrase "could" matters. This technology still needs integration, environmental testing, larger networks, and lower-cost packaging. The current system is not ready to appear inside a smartphone or vehicle tomorrow. Even so, the direction is convincing. Sensors naturally produce analog signals. Light naturally carries enormous parallel bandwidth. Neural networks naturally depend on repeated matrix and convolution operations. The PEIC brings those properties together. It does not wait for the world to become digital before intelligence begins. It starts computing while the information is still light. A camera image becomes a spectrum. A radar echo becomes a spectrum. A pharmaceutical sample becomes a spectrum. One fiber carries them. One chip separates them. One optical network decides what they represent, and one part of that decision responds in 1.33 nanoseconds. So what do you think? Will photonic chips become the standard front end for cameras, radar, and scientific sensors? Or will the difficulty of lasers, calibration, and packaging keep conventional electronics in control? Let me know your view in the comments. And if you want more grounded stories about the chips, materials, and hidden engineering breakthroughs reshaping computing, subscribe to Eastern Engine. Because the next generation of AI may not begin by converting the world into numbers. It may begin by letting light understand the world first.